As a little extension to our discussions on exponential growth, I want to talk to you about logistic growth. Um, we tend to say that populations grow exponentially because in the early years they might. However, in real life, populations tend to follow more of a logistic model. Okay, so imagine you drop a bunch of rabbits on an island, or population of people in a state, or people on the globe. Um, it might get steep and start to multiply quickly for a while, but it doesn't follow this exponential pattern for long. Okay, so at some point, the lake that the fish are in, or the island that the rabbits are on, or the globe that we all live on, starts to run out of space and food and whatever else that we need to survive on in that area. And that's where a logistic model is better. It looks like this. And depending on how many rabbits you drop on the island, how close it is to what's called the carrying capacity. All right, there's a horizontal asymptote called the carrying capacity, and that in the equation is indicated by C. That's the one letter in all those A, B, and C that actually stands for a real world quantity. The A and the B would have to do with the specifics of the island or the country or whatever. But we can look at that equation and right away see what the max is. But if we drop a small amount of rabbits on the island, they will multiply quickly and then they will slow down. You could start this thing here. You know, this could be my y-axis if I dropped that many rabbits on the island. But one way or the other, it's going to level out. All right, and so these we're going to use to talk about population growth in a little bit more of a realistic setting. Okay, so we're going to do an example about the number of fish in a certain lake. So the population of fish after t years is given by this function. $18.80 over 1 plus 1.42 e to the negative 0.037 t. And the stipulation, the domain is t is greater than 0, greater than or equal to 0. So you can kind of see, if you think about the structure of this expression, 1.42 e to the negative 0.037 t. Try to think about it, and this is a little bit advanced, this is more of a calculus idea, but what's going to happen as time passes? As time moves on, e to the negative something is the same as 1 over, let me get that out of the way, I don't want to group that together, but this part is the same as 1.42 over e to the 0.37 t. So we've talked about how a negative exponent is on the bottom. You should know that already. So if you move that exponent to the bottom, you can see as time passes, if you have a bunch of years here, 1.42 over a very big number is approaching 0. As time goes on, this part of the equation approaches 0, and that's how you can see that 1880 is the limit. We're never going to go over 1880 because the bottom is getting closer and closer to 1. I don't want to talk too much about that, but I just want you to kind of understand why 1880 is the carrying capacity, why this lake can hold only 1,880 fish. So the kinds of questions they might ask us are to graph it, or to see how many fish there are at a certain year, or to see how long it's going to take to reach a certain population. But they're almost always going to ask us, how many fish can a lake hold? The answer is 1,880, and that's it. If they ask us, how many fish will there be in 50 years? And we just plug in 50 for t and see. So let's check. Get my calculator back out here. So if I want to know how many fish there will be in 50 years, I need to do 1880 divided by, now this whole denominator needs to be in a set of parentheses, 1 plus 1.42 to the also in parentheses, negative 0.037 times 50, close. I think I got all my parentheses correct. 1, 2, 3, 4. What about that? There should be 1,234 fish in 50 years. Now, a lot of times they'll ask us to graph, so I've gone to my favorite site, Desmos, to look at a graph of this thing. So you can see about a little bit less than 800 fish if you just plop them down in a pond. They're going to start increasing rapidly for the first years, but then it's going to dwindle out. We're not going to keep that pace up because the lake is only so big. There are only so many little baby fish that these fish can eat, or so much seaweed they can eat, or whatever. There's only so much space. You can't keep on increasing fish forever, correct? Let's add in, just to confirm that last one, that question was what happens at time equals 50 years. So let's add in x is 50. You can do these things in your graphing calculator, but this picture might be a little better than your graphing calculator picture. And something has gone wrong. Just a second. Aha, I found it. In my calculator, I forgot the E. I need to do 1880 divided by 1 plus 1.42 times E to the negative 0.037 times 50. Close that, 1536. There we go. All right, found it. Thank you. All right, so at 50, we have 1536. That's a value that you're going to use in your calculator, whether you're typing it in or graphing it and plugging in 50. They could also say at what point will the population, how long will it take for the population to reach a certain amount? So that's what I've graphed here. Y equals 1875. When is that going to happen? Well, the intersection of those 2 points is right there at basically 170 years. All right, so it's going to level out and take a long time, right? This is a long period of time, 170 years. But, you know, I assume that a new crop of baby fish happens every year, and that's going to slowly adjust over time. But that in your graphing calculator, you would graph the function, you would graph y equals 1875 and see where they cross, okay? We don't need to talk a whole lot about this one because you're going to be given the equation, all right? The background of this equation is beyond our level right now, but you should be able to use it. And you know, if you're given A, B, and C, you should be able to sub in an amount of time and get the value of the function, or in your calculator, you should be able to sub in a value for the function and get the amount of time t. So don't worry if you're thinking, where in the world did this equation come from? Just realize we're studying it because it's more realistic than an exponential model, and you'll be given it and just be asked to substitute in x or y's in your calculator. That's it. All right, so that'll do it for Logistic. Young